Oops. This is called diode characteristics. The chapter number doesn't make any difference. These graphs are in your book. I'll have to figure out which chapter it's in. Everybody okay? So this is what we call the characteristic curve for a diode. So a diode is not an open switch, and a diode is not a closed switch. We say when it's forward bias, it acts like a closed switch, and reverse bias, it acts like an open switch, right? Well, in actuality, as soon as I put a forward bias voltage on the diode, we have a very, very small current leaking through it. And then what happens when it starts getting up to the barrier voltage, the barrier potential, it's going to start curving. It don't do this instantly. And then it's going to start an up. Once it's forward bias, then it'll actually go in a slope. Everybody understand why it don't go straight up? Because there's an R component inside the diode. So the more current you put through it, it's going to. So one of the ratings we'll look at, they call it VF max. And of course, this will be the maximum voltage. That should be the voltage you expect to cross it when you're conducting the maximum current. If you're below that, it's going to be below that, right? You understand? Now, when I reverse bias it, what's going to happen is that's going to be the leakage current right there as soon as I do it. And it's going to stay pretty constant right here until you hit this knee right here. And once we call that the knee, by the way. Can y'all see why? Because it looks like a knee. And then it's going to break over. And a standard diode, if you let it do that, and you don't have it protected by a big resistor, which we don't in power supplies, then what's going to happen? Yeah, and that's not an average voltage, that is a peak voltage. So that means we got to deal with, when we're trying to block V, we're going to be blocking V peak, not V average, V peak, right? You understand? And then sometimes in a full wave power supply, which we'll talk about, the diode actually sees peak to peak. So we'll have to make sure we get above that, probably at least about 150%. So what we do, of course, we can't deal with this, because to deal with this, I'd have to know the actual resistance of the diode and all this other kind of stuff. So when we start, so this is forward biased, everybody okay? And then of course what? This is reverse bias, okay? And then of course everybody okay on the symbol? And the forward bias it, we point the cathode toward the negative and the anode toward the positive. If you see on a test that the cathode has to be negative and the anode has to be positive, and if you mark that true, you're going to miss it. Because very seldom are you going to, normally you measure the same potential on both sides. You either measure 0 on one side and a positive potential on the other, 0 on one side and a negative potential, or positive on both sides or negative on both sides. Y'all understand that? If you measure a positive on the cathode and a negative on the anode, if you measure a negative on the cathode and a positive on the anode, you might as well throw the diode away. It's bad. So I've never said that, right? I said the cathode has to be negative in respect to the anode, right? You understand? Or the anode has to be positive in respect to the cathode. They can both be negative or they could both be positive. So we've already looked at this. We know here, this would be forward bias. If this was silicon, we should measure what across the diode? Yeah, we should measure approximately 7/10 of a volt or thereabouts. Over here, we're going to measure via the source minus 7/10 of a volt. Now, sometimes that don't come into play. You know, if I'm dealing with 100 volts, then the 7/10 of a volt means nothing. But if I'm dealing with 5 or 6 volts or 7 or 8 volts, then if you don't take that 7/10, you're going to be off quite a bit on your current calculations and all that other kind of stuff. Right? So these are diodes. They come in all different types of packs. They come in different sizes. They're going to identify where the cathode or anode is. The problem is sometimes they'll put the diode is handleable a lot, or something happens and that little old band wears off. So if the band is gone or the symbol's been wore off, how do you find the cathode and the anode? With a what? With an ohmmeter, right? Everybody understand that? Real easy to identify. Very, very easy. And its drastic consequences, especially in a power supply. Usually in a power supply, if you put the diode in backwards, you're going to create a short circuit. So you better honor the diode. A lot of times they'll put the center, they'll paint it or silk screen the symbol beside that. So we have three approximations we'll use. We have what we call the first approximation, which we treat the diode as ideal, which means we say, okay, if it's forward bias, it drops no voltage. If it's reverse bias, it drops all the voltage. Everybody understand that? We call this the first approximation. Usually if we're dealing with 100 volts or so, we'll use this. If we're dealing with the under 100 volts, or I think it's 50 volts, then we usually use the next one. So what we're going to do in this class, all along, is we're not going to use this guy because we're not going to be dealing with high voltages. We're going to use, so this would be the voltage versus current graph of an ideal diode, of what we call the ideal approximation. And we're not going to use this because we're not going to be dealing with 50 volts. We're going to be dealing with low voltages. Why do we deal with low voltages when we're trying to learn electronics and stuff like that? Because of safety, right? You understand that? So we're going to be well below what they consider to be a lethal voltage. Y'all know what they consider to be lethal? 50 volts. Maybe 50 volts RMS or 50 volts DC, because your body don't see peak. It don't mean it's lethal. It's just considered to be, it has the ability to be lethal. Of course, the higher the voltage is, the more lethal it becomes. We're going to use what we call the second approximation, also called the practical model. So what we do is we show the barrier potential. So if it's forward bias, we're going to subtract 7/10 of a volt. For silicon, we're going to subtract 3/10 of a volt for germanium, and we're going to consider reverse bias to be perfect. Everybody okay? And so we're going to use the second approximation. So this is what we're going to use right here. We're going to use this VI characteristic curve right here. We call this the VI characteristic curve because it's voltage relative to current, right? Everybody okay? Now, of course, if I was an engineer and I really was critical about things, I needed to know exactly the voltage and everything, then we would use what we call the third approximation. We're not going to use this in the class, or it's called the complex model. This is where you would build the charts, you would look at the resistance of the meter, you'd do all this and actually build that curve to know exactly what that diode was doing at a certain voltage at a certain current. Odds are there's very few people that have to use this because usually second approximation works great. Especially when you're dealing with resistors and capacitors and stuff like that, because those values on all of our components are approximations, right? You understand that? So if I've got a 1K ohm resistor in my hand, what's the likelihood of it measuring exactly 1K? It's probably more unlikely than it's likely, right? So every one of our devices has a tolerance. So that means a second approximation is usually just fine for everything that we do. It's going to get us in the ballpark so that we understand now that if I make a voltage measurement, I calculate it and I make a voltage measurement, the voltage measurement will never be the same, but it's going to be close so I know whether it's what, right or wrong. Everybody understand that? So this is third approximation, which we're not going to use, thank goodness. And everybody okay? So testing a diode, using a multimeter to check a diode. If we're using an ohm meter, we're looking for a real high split, right, ratio between the forward bias and the reverse bias. It's still going to measure K. But one way it might measure K, 100K, another way it might measure meg, right? You understand? As long as we get that big old ratio between the forward and reverse bias, then it's okay. Now on old analog meters, if you've got an old analog meter, a pointer meter, sometimes they reverse the polarity. So the red lead is actually the negative and the positive lead is actually the positive. Did I say that right? The red lead is a negative and the black lead is a positive. So you need to check a couple of diodes that you know that's good to make sure that the polarity of the meter's right. On new meters, you don't have to worry about that. So if you got a digital multimeter, the red lead will be the positive and the black lead will be the what? The negative. So reverse bias, we're going to show a very high resistance, or it's going to show an open. This is the black lead on the anode and the red lead on the cathode. Forward bias, it's going to be relatively low. When we say it's low, we don't say it's low, we say it's relative. It's relative to what? It's relative to the reverse, right? You understand that? If you're checking it with a regular ohm meter. If you're checking it with an ohm meter that has a diode scale on it, then that's what's so neat, because using most digital multimeters, they have a special scale for testing silicon and germanium diodes. They have a test. We can't do LEDs. Why? Because they're not made out of silicon and they're not made out of germanium. They're made out of derivatives of gallium, which is another semiconductor. And they have a VF that's pretty high, usually around 2 volts. So usually our meters will not break that over. So you cannot check an LED with this meter. The only way you can really check an LED is to put a battery in series with it or put it in a circuit. Of course, if it's working in a circuit, it's pretty obvious because it's going to do what? It's going to light up. The scale is usually represented with the diode symbol. Y'all know the symbol now, right? And what's it going to do for us? It's going to measure the approximate VF. But remember, your meter's putting out almost no current at all, so usually it's going to measure lower than what it will actually be in a circuit. Are you okay? But you know it's good, and you know basically an idea whether it's germanium or silicon. We just have a little problem with these big old diodes because they're doped so heavily because they're dealing with a lot of current that their VF will be a little less. So we okay on this? So this is showing. Now what you need to do, this shows 2.6 volts, but what you need to do is look what your meter shows you when you don't have it connected to anything, right? You'll understand. And then hook it up to your diode. So some of your newer meters actually puts OL up there when you reverse bias. This meter, which is an older meter, measures about 3 volts when it's reverse biased. So this one on the left is bad, right? The one on the right is bad. I mean, on your left. One, this is bad. Why? See, so it's showing me what's open. If it shows low both ways, then that means you got a problem. It's very leaky. So diodes can go bad. They can become leaky, which means they're going to conduct current when they're not supposed to be conducting current. Or they could go open, right? You understand? Or they could short. Diode short. But it's real easy to find with an ohm meter. With an ohm meter. And by the way, it's still measuring voltage, but we still call it an ohm meter because that's all. It's still the ohm meter function, but instead of converting it to ohms, it's actually showing you what the volts that the meter had to step it up to cause the current flow. And we're not going to get into this. We'll come back to this later on. This shows you how to a little bit of troubleshooting in power supplies. So that's what I want to show you. So what are we going to use in all our calculations? We're going to use what we call second approximation. Because the load does not see what's on the input of the diode, the load sees what's on the output of the diode, and that'll be after the event. This is what we're going to do Monday. We'll come in and we'll hook up a diode. We'll put a resistor in series with it. We'll start changing the voltage real slow, and we'll explain what we got to do. The problem we have with most variable power supplies is they don't go down to 0. So what we'll do is we'll show you how to wire a potentiometer. We're going to use a potentiometer. Y'all know what a potentiometer, we use the potentiometer for? To control what? A voltage. Not regulate, control the voltage. They don't regulate it at all. But what we can do is if I've got a 10 volt power supply, if I hook up a pot right, I can get anywhere from 0 to 10 volts. 0 to 10 volts out of the wiper of the pot. So we'll have to do that with our power supplies. And what we're going to do is we're going to start off with forward bias of diode. We're going to start off with 0. We're going to measure across the resistor. And what we're going to do while we're measuring across the resistor is we're going to use it to calculate current. So we're not going to have to use an ammeter. We're going to use the resistor to calculate the watt current. And we're going to slowly increase the voltage up. And we're going to start getting current flow. And then we're going to create this graph right here. And then we're going to all get together. We're going to come up here and hook up about four power supplies. This thing won't break over to well over around 90 volts, and 90 volts is pretty dangerous. So we'll do this as a class. We'll put a 10 gig ohm resistor in series with it, so we can break it over. We'll measure the voltage drop across that resistor. We won't use 10. We'll explain it when we get into the lab for obvious for reasons y'all probably don't understand. We'll measure the voltage across the resistor. We'll calculate the current. Then when we get it broke over, we'll come up and we'll take a soldering iron, put it up next to it. We should expect the current to go up. We'll get some freeze spray and spray on it, and the current's probably going to go to almost 0. So we'll see that the that reverse current is controlled by temperature. Right? So the forward current is controlled by it being forward bias. We don't get it hot enough to shake it through a lot of minority carriers on the forward bias situation. But that reverse bias, that's when we can really cause problems with temperature. So semiconductors, we have to watch the temperature that we run those things. Vacuum tubes didn't care. Vacuum tubes, I mean, them suckers ran. We heated them up to make them work. So vacuum tubes literally have to heat. We have to heat them up to make them work. So they didn't care. But semiconductors, because of this reverse bias and this kind of stuff like this, they're rated at a temperature range. Usually it's pretty warm. It's about 70 degrees centigrade is the maximum they're rated at. But compared to other things in vacuum tubes, that's way, way down. So this is the lab we're going to do Monday. So make sure you bring in your meter, bring in your safety glasses, and bring in your lab book. It's the same lab book you used in what? In DC. So you should already have your lab book. You might not have your meter. This is where you have to buy your meter, or you need to buy it in your AC in this class right here. Your meter, we require you buy one of those because that is your tool of the trade, right? You understand that? If you're in this field, you're going to need a meter. And a lot of places you go to work for don't provide them. US Steel does. They provide really good meters. They provide flukes. I don't know what they are. True RMS meters. Even those guys probably never use it. I think they paid about $450 for those meters.